Hey everyone, welcome back to Wrath of Math. In today's video, we'll be going over a proof that if a graph has no odd cycles, then it is bipartite. This is a viewer-requested video. I always appreciate those viewer requests, so be sure to leave your requests down in the comments. I want to begin by mentioning that this statement goes both ways. So a graph has no odd cycles if and only if it is bipartite. So if a graph has no odd cycles, then it is bipartite, and if a graph is bipartite, then it has no odd cycles. However, it's quite a bit easier to prove this direction, that if a graph is bipartite, then it has no odd cycles. So in this video, we're focusing on the more difficult direction, that if a graph has no odd cycles, then it is bipartite. So let me go ahead and circle that, so we know what we're talking about. We're not talking about this, we're proving this. This proof is a little long, but I hope you'll stick with me, and I think we'll have a lot of fun going through this proof. As I always say in my proof videos, I do not write out the proof for you. I don't think that'd be very fun for either of us. Instead, I try to give you the mathematical ideas and explanation that you need to know to formalize the proof yourself. So we'll go through the mathematics behind the proof, but I'm not writing the whole thing out. That would be a very boring video. Alright, so let's get into the proof, and the first thing I want to mention is a very important statement we need to know right off the bat. And that is, a graph is bipartite if and only if all of its connected components are bipartite. This is important because it means we only have to prove our claim for connected graphs, because if a graph is disconnected, we could just apply our proof to all of the connected components, and if all of the connected components are bipartite, then the whole graph is bipartite. So we just need to consider connected graphs. And I think this statement is pretty intuitive, so if you can't accept it at face value, take a couple minutes to jot down a proof of it, or just think through the proof in your head. But we're going to continue having accepted this statement. And so, we can begin our proof like this. Let G be a connected graph with no odd cycles. And to begin our proof, we're also going to want to identify a vertex of the graph G. So let's let W be an element of the vertex set of G. And we can assume that G does have a vertex, because if G doesn't have any vertices, then it is trivially bipartite, and we don't really have anything to prove. So again, we're just letting W be a vertex of G. For this proof, we're basically going to show that the graph G is bipartite just using the definition of bipartite, which means we're going to partition its vertex set so that every edge of G joins a vertex from one set to a vertex in the other set. But how are we going to do that? We barely know anything about the graph G, so how could we possibly partition its vertex set in this very special way? Well, to get some idea of how we might do this, let's quickly take a look at a similar problem. I'm showing you this because this is a very valuable strategy. We're trying to solve a problem, and one way we might be able to make some steps towards solving that problem is by looking at a similar problem that we know the solution to, or that we can find the solution to. So here is our similar problem. This is a connected graph with no odd cycles, just like our graph G. And we're going to try to partition the vertices of this graph into, let's say, a red group and a green group, so that no vertices in the red group are adjacent and no vertices in the green group are adjacent. And that's exactly what we're trying to do with the graph G. So if we can find a method to solve this problem, that same method might work in our proof. So let's try to partition these vertices, starting with this one. Should this go in the red set or the green set? Well, it doesn't really matter since we haven't placed any of the vertices yet, so let's just call it red. So I will color this one red. And I'm also going to label it 0, because it is a distance of 0 from itself. And going on, I'm going to label each of these vertices with their distance from this starting vertex. Alright, now the next vertex, should it be red or green? Well, it can't be red because it's adjacent to this red vertex, so it's gotta be green, and we label it 1 because it's a distance of 1 from this vertex. Now the next vertex, red or green, we know it can't be green because it's adjacent to a green vertex already, so it's gotta be red, and it is a distance of 2 from this vertex. And I think you see how this is going. The next vertex has to be green because it's adjacent to a red vertex, and it is 3 away from the starting vertex. And then the last vertex has to be red because it's adjacent to a green vertex, and it is a distance of 4 from the starting vertex. Alright, so now we've found a partition of these vertices that demonstrates that this is a bipartite graph, because none of the red vertices are adjacent and none of the green vertices are adjacent. Now, what do all of the red vertices have in common? And what do all of the green vertices have in common? Well, perhaps you notice the red vertices are an even distance away from the starting vertex. Meanwhile, the green vertices are an odd distance away from the starting vertex. So right there, folks, that is our method. We split the vertices into 2 sets depending on the parity of the vertices' distance from a single vertex. So let's try using that same method to partition the vertices of G. We'll call the first partite set X. We'll say that X contains all vertices of G, all vertices V of G, such that the distance from each vertex V to the vertex W is even. And remember, W is that vertex of G that we selected at the start. And then the other partite set we'll call Y. You can imagine what this is. This is the set containing all vertices of G, such that their distance from W is odd. And again, this is the exact same way that we partitioned these vertices, and it worked once, so maybe it will work again. There are 2 things we need to make sure are true so that we know that this is a valid partitioning of the vertex set of G. The first thing, let me write in a different color here, is that X and Y can't have any common elements. So the intersection of X and Y has to be the empty set. And we know that this is indeed true, because every vertex has exactly 1 distance from the vertex W, and that distance is either going to be even or odd. So there's no way a vertex can be in X and Y, which means they have no common elements, so their intersection is the empty set. The second thing we need to know is that every vertex of G is in X or Y, so X union Y has to be equal to the vertex set of G. We also know this is true because remember, G is a connected graph, which means that every vertex of G is going to have some defined distance from the vertex W. That distance will either be even or odd, so that vertex will either be in X or Y. So this is a valid partitioning. Every vertex is in exactly 1 of the sets, and no vertex is in both of the sets. But this does not mean that this is a bipartite partitioning. That's what we have to prove next. In order to show that this is a bipartite partitioning, we need to show that every edge of G joins a vertex in X to a vertex in Y. In other words, no edge can join 2 vertices in X, and no edge can join 2 vertices that are in Y. So what we're going to do is proceed using contradiction, which is a very powerful proof method. So let's suppose, for the sake of contradiction, that this is not a bipartite partitioning. And what would that mean? Well, that would mean that there exists 2 vertices we'll call A and B. A and B are either both in X, or A and B are both in Y. So there exists these 2 vertices, either both in X or both in Y, that are joined by an edge, so such that AB is an element of the edge set of G. So the only way that this is not a bipartite partitioning is if there exists 2 vertices, both in X or both in Y, that are joined by an edge in the graph G. So that's why we assume this for the sake of contradiction. We're going to show that it can't possibly be true, and that will demonstrate that this is in fact a bipartite partitioning. So one more time, because this is really important, we're assuming that there exists 2 vertices, A and B, that are both in X or that are both in Y. It doesn't matter which, the proof will proceed the exact same way, and we're assuming that these 2 vertices are adjacent. Alright, so let's get on with it, and I'm going to begin by addressing one specific possibility. What if A or B is equal to that first vertex W? Let's address this possibility. If without loss of generality, which I'll abbreviate WLOG, if without loss of generality, A is equal to W, and I put without loss of generality because this argument will proceed the exact same way whether A is equal to W or B is equal to W. And we know they can't both be equal to W because they are joined by an edge, so they have to be distinct vertices. Alright, so if A is equal to W, then the distance between A and W, is equal to 0. And remember that 0 is even. So this means that the distance between B and W has to be even as well. Because remember, we assumed that A and B are either both in X or they're both in Y, which means that their distances from W have to either both be even or they have to both be odd. Remember, that's just because of how we defined X and Y. So if A is equal to W, then the distance from A to W is 0, and since 0 is even, this means that the distance from B to W has to be even as well. But we could go a step further. Since W is equal to A, this also means, this also means that the distance from B to A is also even. But this is not possible because we assumed that A and B are joined by an edge. So they are adjacent vertices, which means that the distance from A to B is equal to 1, and 1 is not even. So by assuming that A and B are adjacent, we have assumed that the distance between them is 1. But if one of them is equal to W, that means that their distance has to be even. This can't be the case. So we have demonstrated that A cannot be equal to W and B cannot be equal to W. So I'll write that now. Therefore, A is not equal to W and B is not equal to W. So the important point to take away from all that is that A is not equal to B, and neither of them are equal to W. We know that A is not equal to B because they are joined by an edge, so they have to be distinct vertices, and we know they're not equal to W because of this argument we just went over. So because of all that, we can draw this beautiful diagram that we'll use to illustrate the rest of the proof. Let's say we've got our vertices W, A, and B. The whole family's here, and I'll move this down just a little bit. Remember that G is a connected graph, so there is some shortest path from the vertex W to the vertex A. We'll call that path P. So let P be a shortest WA path. So this just means that there is no shorter way to get from W to A. There might be another way that's just as short, but there is no shorter way. And by the same logic, there is a shortest path from W to B, and we'll call that path Q. So let Q be a shortest WB path. An important fact we need to remember is that the length of P and the length of Q have the same parity. And remember, this is because A and B are either both in the set X or they're both in the set Y, which means that their distances from W are either both even or both odd. So the lengths of the shortest paths from W to A and from W to B also have to be both even or both odd. And we're closing in on the end here, so stay with me. We know that P and Q have at least one vertex in common, because they both start at W. But they might also have another vertex in common. So let's just label this point here, we'll call this X. And we're going to let X be the last common vertex of P and Q. And it may be the case that X is actually W, but the proof will proceed the same way even if that's true. So now we have split these two paths into two different pieces. Let's call this first part of P, P1, and we'll call the second part P2. And similarly for Q, we'll call this part Q1 and this part Q2. Now let me move this over to the side so we've got a bit more room to write. What do we know about the length of Q1 and the length of P1? The length of Q1 and the length of P1. How do these numbers relate? Maybe you figured it out by taking a second to think about it. These lengths have to be equal. This is because both of these paths are shortest paths from W to A and from W to B. So if Q1 was shorter than P1, then we could actually get from W to A faster by traveling across Q1 and then traveling the rest of the way to A. Similarly, if P1 was shorter than Q1, then we could get from W to B faster by traveling across P1 and then traveling the rest of the way to B. And neither of those things can be the case, because we already said there's no shorter path from W to A, and there's no shorter path from W to B. So we know that the length of Q1 is equal to the length of P1. And another fact that's pretty obvious, but also pretty important, I'll point out, is that the length of P is equal to the length of P1 plus the length of P2. And similarly, the length of Q is equal to the length of Q1 plus the length of Q2. Remember that the length of P and the length of Q are either both even or both odd. So since P1 and Q1 have the exact same length, that means that the lengths of P2 and Q2 have to both be even or both be odd. Because if one was even and the other was odd, then the length of P and the length of Q would not have the same parity. One would be even and one would be odd. So let's write that down, because that's another very important fact. The length of P2 and the length of Q2 have the same parity. Alright, now we're almost done. You might notice that our diagram is actually missing something very important. Remember that we assumed, let me scroll up here, we assumed for the sake of contradiction that there was an edge joining A and B. So let's draw that in our diagram, an edge joining A and B. And now we can start to consider this cycle. This is the cycle that travels across P2 in the opposite direction, which I'll denote like this, P2 inverse. Then it travels across Q2. So it goes like that, P2 inverse to Q2, and then it travels to the vertex A, just like that. So this is just a way to denote that cycle. It starts at A, and then it goes all the way back around, coming back to A like a cycle does. So what is the length of this cycle? Well, let me put those bars on there. What's the length? Well, clearly, it's the length of P2, plus the length of Q2, plus 1, because you've got that one extra edge there from A to B. But remember, the length of P2 and the length of Q2 have the same parity. When you add two numbers of the same parity, whether they're both even or both odd, you get an even number. And that's another easy thing to prove, so if you're not familiar with that fact, go ahead and jot down a little proof of it. But that means that we can rewrite this as 2k plus 1 for some integer k. Again, this is true because this number and this number have the same parity. So when we add them, we are going to get an even number. This 2k is just a generic way of representing that even number. Well then, this number here, 2k plus 1, by definition, that is an odd number. And let me just write a little arrow and note there, because that is really the mic drop moment. That is odd, which means this cycle is an odd cycle. And that, my friends, is a contradiction, because remember, way back at the beginning, we assumed that our graph had no odd cycles. So, by assuming that two vertices in X are adjacent, or two vertices in Y are adjacent, this supposition we made here for the sake of contradiction, by doing that, we forced the existence of an odd cycle, which is a contradiction because we assumed way at the start that our graph has no odd cycles, which means that there cannot be any adjacent vertices in X, and there cannot be any adjacent vertices in Y. So this is indeed a bipartite partitioning of the vertices of G. We have shown that G is bipartite by partitioning its vertices into two sets that have no pairs of adjacent vertices within them. There's no pair of adjacent vertices in X, and there's no pair of adjacent vertices in Y, because if there was, that would lead to a contradiction. Oh man, that was a fun one. So I hope this video helped you understand how to prove that if a graph has no odd cycles, then it is bipartite. Thank you very much for watching. Be sure to let me know in the comments if you have any questions, need anything clarified, or have any other video requests. I'll see you next time, and be sure to subscribe for the swankiest math lessons on the internet.
Entertain a lonely fly, buzzing around in my ear. He listens to my mind. Maybe it's all come to pass, every disaster I know.